The universe is not static, it never has been. But for most of human history that's exactly what we believed. Look up at the night sky. The stars don't seem to move, the constellations stay the same night after night, year after year. The moon glides smoothly, the planets wander a little but always return. To ancient eyes it all felt permanent, still, like a great cosmic painting hung above the world. So we built our understanding of the universe on that stillness. The Earth we thought must be the center, solid and unmoving. Everything else, the sun, the stars, the heavens, must be spinning around us. A perfect celestial dance set in motion by something divine, but always repeating. For centuries this view held not because people lacked imagination, but because it worked. For millennia, the dominant view of the universe had placed Earth at its absolute center. But it was in the Hellenic world that this idea became a technical cosmological model, and the man who did that was Claudius Ptolemy. Ptolemy lived in Alexandria around the 2nd century CE. He was a scholar, a mathematician, and more than anything, an astronomer who wanted to make sense of the skies with numbers. He compiled, organized, and refined it into a systematic model of the cosmos, laid out in a massive work known as the Almagest. In Ptolemy's model, Earth sat at the very center of the universe, perfectly still, unmoving. Around it, in concentric spheres, revolved everything else. To fix retrograde motion, Ptolemy introduced epicycles. These were small circular paths that each planet traveled while that entire smaller circle orbited Earth. This looping motion could recreate the backward steps seen in the sky. It all began quietly in 1543, with the publication of a book that would shake the foundations of astronomy. Its author wasn't some famous scientist. He was a priest. His name was Nicholas Copernicus. Born in what is now Poland, Copernicus studied law and medicine, but his real passion was the sky. For years he had been quietly collecting observations, running calculations. In it, he outlined a model of the universe where the sun, not the Earth, was at the center. Based on his observations, Copernicus proposed 3 distinct motions of Earth. First, Earth rotates on its axis every 24 hours. Second, Earth orbits the sun once per year. That revolution around the sun explains the changing positions of the planets and the seasons. And third, Earth wobbles slightly, tracing a small circle while it moves through its orbit. Then came the telescope. It wasn't invented by a scientist. It started as a Dutch novelty, just a few lenses slapped together by spectacle makers. But when news of this strange device reached Italy, one man saw more than just novelty: Galileo Galilei. In 1609, Galileo pointed it to the heavens, and what he saw would rattle the old order. First, he looked at the moon. It wasn't the perfect, smooth, divine orb that the ancients had believed. It had craters, mountains, shadows. Then he looked at Jupiter, and there dancing around the planet were 4 small points of light. These were moons. Moons orbiting something other than Earth. Then he turned to Venus, and that sealed it. Venus went through phases like the moon, proving it orbited the sun. Johannes Kepler was a German mathematician and astronomer. He got his big break when he became assistant to Tycho Brahe, the last great naked-eye astronomer. Brahe spent decades collecting the most accurate measurements of planetary motion ever made, all without a telescope. When he died in 1601, he left all of his data to Kepler, and Kepler dove in. Kepler discovered that planets don't move in perfect circles at all. They move in ellipses. That was his first law. Planets don't move at constant speeds. They sweep across space faster when closer to the sun. That's his second law. And then came the third law. The further a planet is from the sun, the longer it takes to complete one orbit. The next generation asked, why do planets move at all? That's where the famous falling apple came in. Newton gave this invisible force a name: gravity. He realized that the same force that made apples fall also held the moon in orbit, kept Earth circling the sun, and ruled the dance of planets. Using Newton's law, we knew that Earth orbits the sun at about 107,000 kilometers per hour. Mercury moves even faster because it's closer. William Herschel was born in Germany and moved to England as a composer, but he had an obsession: telescopes. He started building them, grinding mirrors better than almost anything else of his time. When he pointed those telescopes toward the heavens, he didn't just look, he counted. He and his sister Caroline began a massive survey. He constructed what he thought was the shape of the universe, a flat stretched-out disk like a grinding wheel with the sun roughly near the center. Jacobus Kapteyn never saw himself as a revolutionary. But what he did with numbers changed our understanding. He started collecting data on proper motion. The stars weren't just drifting randomly, They moved in patterns. Two general streams, like cosmic currents, seemed to flow across the sky. The pattern only made sense if the sun was moving, headed toward a point in the constellation Hercules at about 20 kilometers per second. Edwin Hubble enters the picture. Using the Hooker telescope on Mount Wilson, then the most powerful telescope on Earth, Hubble focused on Andromeda. In 1923, he spotted something crucial inside it: a Cepheid variable star. Thanks to Henrietta Swan-Leavitt's work, that pattern could calculate distance. Andromeda was way beyond the edge of the Milky Way. For centuries, we thought the Milky Way was the entire universe. Now it was just one galaxy among many. Jan Oort took a closer look at stellar motion. If the Milky Way rotated like a solid wheel, every star should move at the same speed. But they weren't. Our sun is about 30,000 light-years from the galactic center, and moving at over 200 kilometers per second. At that speed, the sun takes 225 million years to orbit once. To answer what we're orbiting, astronomers turn to radio waves and the Very Long Baseline Array. The VLBA links 10 radio telescopes to form one super instrument capable of resolving incredibly small movements, like spotting a coin on the moon from Earth. All that motion pointed to the same place, Sagittarius A star. Its mass was over 4 million times that of the Sun, smaller than Mercury's orbit. The only thing that fits those numbers is a supermassive black hole. That's what anchors the Milky Way while every star swirls around it. A car comes racing toward you, its engine roaring. Just as it passes, it changes pitch. That's the Doppler effect. Light does the same thing. If a galaxy is moving away, the light gets stretched toward red. That's redshift. Edwin Hubble found that most galaxies were moving away from us. The farther away, the faster they receded. Space itself was expanding, but not every galaxy is running away. There was one that stood out, Andromeda. Instead of being redshifted, Andromeda's light was blue-shifted, meaning it was heading toward us. Fast forward 100 years, technology confirmed it. Andromeda isn't just approaching, it's on a collision course with the Milky Way. The universe is in constant motion. We're spinning, orbiting, flying through space, all while being pulled by forces we can barely see. The old picture of stillness is gone forever.